Hello everyone, my name is Tony Hallam and I'm a PhD student from Heriot-Watt University. Today I'm going to be walking you through a case study of the Volve field, which is an open subsurface dataset released by Equinor in 2018. I also want to acknowledge my co-authors, Colin Macbeth, Roman Chasania and Hamed Amini, who have provided support and guidance on this work. The work I will present was developed independently of Equinor and represents our unique perspective. However, post-study exchanges with Equinor confirmed they had used a similar approach during their operatorship of the field. While at times there are similarities, our investigation and conclusions differ in a number of ways that I will highlight throughout this presentation. During this talk, I will cover an introduction to the dataset, including structure and reservoir geology, as well as the field production history. I'll then move on to our 4D modeling and calibration of the 4D signal and the accompanying 4D interpretation. And finally, I'll tie back the 4D calibration to the observed 4D signal with hypothesis testing using 4D well synthetics before finishing with some conclusions. Volve was a small oil field located in the South Viking Graben area of the central Norwegian North Sea, located adjacent to the Sleipner Vest field and about 200 kilometers west of Stavanger. The field was discovered in 1993 with estimated oil in place of 24.5 million cubic meters. That's about 154 million barrels. The Jurassic reservoir was the secondary target, with the younger Heimdall Formation target coming in dry. Although discovered in 1993, uncertainty in the true resource potential delayed development until after a second 3D seismic survey was acquired using ocean bottom cables in 2002. The initial phase of development spanned June 2006 to July 2009, resulting in 3 production and 2 water injection wells. The wells F12 and F14 were initially strong producers with combined production of almost 9,000 meters cubed per day. But water encroached early, which we see here in the pale colors, quickly displacing oil production from late 2009 and persisting for the remainder of the field life. Primarily of interest to this study is how to derive value from the seismic monitor, which postdates water arrival at the 2 main producers by almost a year. Later we will see how this delay in the monitor acquisition means flood fronts or pathways are not easily mapped, but that value can be derived by building confidence in the 4D vertical sweep pattern by integrating our understanding of the reservoir, the expected 4D response, and the available production logging. Equinor also recognized the need for 4D acquisition to play a role in identifying vertical sweep within the reservoir. They undertook 4D feasibility modeling studies to test this hypothesis based upon the early 2009 production logging. They predicted that differentiation of the vertical sweep would be possible in thicker parts of the reservoir, providing part of the justification to acquire 4D seismic data. Where our approach differs is that we perform a retrospective validation of the 4D seismic signal using 4D well synthetics and production logs from the 2010 production logging campaign. Here we are looking at a schematic semi-regional cross-section going from west to east, modified from Thompson et al. The Jurassic section sits slightly shallower at Volve than in the adjacent Sleipner Graben. The trap is a small, faulted anticline where syndepositional structuring and later erosion by the BCU have resulted in a variable reservoir thickness of 10 to greater than 100 meters. The Hugen itself is of nearshore marine-type facies and considered a transgressive unit, retreating to the south as marine incursion occurred. The overlying Upper Jurassic continues this trend, becoming progressively finer grained and culminating in the Draupner Formation marine clays that are also considered the source rock for the field. The Volve reservoir is isolated from much of the surrounding Hugen Formation by large offset faults to the north, east and south, and to the west the reservoir thins and is either absent or disconnected by the faulted terrace. Some internal faulting occurs, but it is most pronounced between the main block and north block, and on the eastern flank where the reservoir dips steeply through a series of domino-style faults. Although the reservoir is broadly isolated, There is a minor connection to the aquifer leg in the northeast. This had only a minor impact upon production, with water injectors required to maintain pressure in the reservoir. The two phases of production well drilling are highlighted separately. The first phase in 2007 is dark green and targeted the main block and all reservoir intervals. The light green wells were drilled in 2013 primarily to extend field life through improved oil recovery. Looking at a seismic amplitude section through the reservoir structure, we see the thinning nature towards the west of both the reservoir and the Upper Jurassic. Imaging of the top and base reservoir is generally poor. At the crest of the field, wavelet interactions and the strength of the Draupner reflector complicate the reservoir response. Away from the crest, the overlying heather formation has a poor impedance contrast with the Hugen reservoir, resulting in weak reflection events. The underlying Sleipner formation is generally a more confident pick, but correlation across faults can be difficult due to poorly defined internal events and the discontinuity of the deeper salt interface. Although not the focus of this talk, it is useful to consider the expected 4D response at Volve before jumping into the 4D data itself. Previously, we have developed a 4D petroelastic model using well log and core data coupled with a genetic algorithm to optimize for unknown mineral moduli and rock model tuning parameters. From this, we observed that Volve is a relatively stiff reservoir, and over the anticipated range of changes for pressure and saturation, we can mostly expect changes in acoustic impedance to be related to changes in saturation, as indicated by the vertical nature of these 1% impedance change contours. For the subsequent work, we therefore assume constant pressure in forward modeling for the purposes of simplifying 4D interpretation. Now we move to the 4D seismic response. Here we show a typical 4D quadrature difference dip line of the field. This traverse covers the southern end of the field intersecting the F4 water injector. The dominant level of 4D noise is high in this dataset, around 25% NRMSD. We consider the primary signal to be this hardening event. It is relatively continuous, but without the top and base surfaces of the reservoir to guide the eye, it's not always readily obvious. 4D noise beyond the reservoir, both above and below, is quite strong, and we note the especially strong continuous response here of the Draupner where no reservoir production has occurred. The signal clearly impacts the reservoir over the crest of the field, where onlap and erosion occur. If we now take the sum of positive amplitudes from this volume in the reservoir interval, we can see that the 4D response is more or less covering the whole reservoir, denoted by the red polygon. The sum of positive amplitudes, or SPA attribute, may seem like an odd choice here due to the variable thickness of the reservoir. However, I like it in this case for a few reasons. Even though the reservoir is thinner towards the west, we can see at the crest of the field the strength of the 4D response. This is related to the interference of the Draupner as it onlaps the reservoir in these locations. Whilst we expect some amount of sweep in this location, we do not expect it to be as much as down near the water injectors, for example. You also get an idea for the fluid flow edge of the reservoir, which is less apparent in a mean amplitude map, for example. So back to our original question. How do we derive value from the 4D signal, in this case when the signal pervades most of the reservoir? Typically, one might look for areas of undrained reservoir. This area between F14 and F5 looks promising, but it is also an area of intense faulting, so it might just be imaging related. And the rest of the reservoir, apart from this north block, looks more or less accessed by the existing wells. We might also consider saturation or facies mapping based upon the amplitudes, but the Draupner interference significantly reduces confidence in the quantitative representation of these amplitudes. Let's step back from the 4D for a bit and consider the reservoir stratigraphy. From a porosity perspective, the Hugen is more or less a blocky sand with some interbedded, fine-grained layers and carbonate lenses. From a seismic elastic perspective, the reservoir is pretty homogeneous, and the overall reservoir is thin enough that we don't see these intra-reservoir layers in the 3D interpretation. However, from a fluid flow perspective, there is a strong horizontal to vertical anisotropy to the overall reservoir. In particular, are two sands within the center B zone of the reservoir which can act as very high permeability conduits between injectors and producers, so-called thief sands. This scenario was confirmed using production logging. Here we show a producer-injector pair with a schematic of the reservoir architecture. Production logs for two wells are shown. At the producer, we see from the saturation log left that sweep, blue replacing black, has been effective from the base of the reservoir. However, the PLT, right, at measure of wellbore flowing volume, indicates the majority of production is coming from the completion at the top of the thief zone. The injection well saturation log, which unfortunately ends near the top of the lower Hugen, shows good sweep in the middle Hugen, but not in the upper Hugen. The result of this is possible bypass pay in the upper zone, and targets for IOR, which is exactly what Equinor did and confirmed in Phase 2 of the field's development. Consider now how this relates to the 4D seismic. If we overlay a 4D traverse between these two wells, we might get something like this. Although our seismic stratigraphy does not connect the wells by straight lines, I hope you can visualize how the blue hard response approximates the water sweep from the injector to the upper part of the producer. To build confidence in this interpretation and to consider whether additional insights can be made, we move on to 4D well synthetics. One of the better ways to gain a handle on the value in a hypothesis is through 4D synthetic modeling. In all cases, we are going to use the same well, the water injector F4, and the same wavelet, a zero-phase, statistically generated wavelet from near the wellbore on the baseline survey. A 20 Hz Ricker wavelet is also plotted for comparison. The reservoir here has approximately 100 meters vertical thickness. We have clear differentiation between the upper, middle, and lower reservoir zones. Remembering that our key units for fluid flow are the two thief sands in the middle zone. We can also see the permeability heterogeneity, which is going to affect vertical sweep and is the focus of our modeling study. In the first case, we show the result with blocky perfect water sweep. This is similar to what might have been done in feasibility work before measures of saturation in production logging RST runs were available. The result is a strong trough peak at the top of the reservoir. Remember, this is a 4D quadrature difference of the two saturation cases, so the event appears inside the reservoir. There are less strong events in the lower part of the reservoir. Adjusting this case to only sweep the middle thief zones, we note significant changes to the response. The upper and lower troughs are now focused on the central zone, where water sweep has occurred. There are also strong negative side lobes associated with the unswept zones. This looks reasonably similar to the type of signal we observed on the flow schematic and 4D quadrature example section. In the third case, and based upon the PLT-RST results, what one would consider the most likely, we observe a similar distribution of events, but a softening of the lower peak trough pair. The gradual transition caused by the elevated initial water saturation at the base of the well means a hard boundary is needed in the saturation changes to generate a strong trailing trough. This observation will be important later because this strong trailing trough is visible across much of the reservoir. We will also reduce our section view of the seismic to a radial seismic extraction at the wellbore. Aspects of these models seem to match the observed 4D, but none are a great fit. Keeping the OWO model from before, which had an OK match at the base of the reservoir, let's now introduce the 2010 RST data, which was logged 1 month before the 4D seismic survey. The RST data shows the impact of permeability on sweep. Particularly in the middle zone, we now see a bifurcation of the doublet peak indicating sweep and a reduction in amplitude of all events. The lower peak is also moved deeper as we introduce sweep into the upper part of the lower reservoir, better aligning with the observed data. In the third scenario, we reduce sweep in the upper thief sand to approximate the observed seismic. Reducing the sweep seems odd, but a couple of things could be going on here. RST logging through casing is not perfect, and the saturation changes may be localized to the near bore, with the intra-thief shale zone preventing sweep, because the perforations are in the lower half of the reservoir. This possibly suggests that while the production logging near the crest shows efficient sweep of the upper thief zone, this may not be the case down dip where vertical barriers to flow are better developed. Finally, we consider alternative sweep efficiency options for the lower reservoir unit. As the sweep efficiency increases in the lower reservoir from left to right, we observe a decrease in the strength of the lower reservoir seismic trough. This is the same effect as we modelled with the blocky results a few slides back. This suggests, at least with this model, that to generate the strong trough, sweep in the lower zone should be relatively poor. Thus, a final synthetic 4D tie, with the required water sweep to generate it. The 4D seismic appears to validate the unswept nature of the upper Hugon. This also matches the interpretation from Equinor and their second phase of drilling, which used geosteered laterals to target bypass pay in the upper Hugon. The modelling appears to disagree with the RST, and the upper thief sand and sweep, at least down dip of the producers, may not be as efficient as the production logging suggests. Matching the strong trailing trough of the lower Hugon is challenging. Some sweep is required in the upper part of the lower reservoir to match the zero crossings between observed and synthetic, but a strong oil saturated lower Hugon is required to generate the trough. I've experimented with increasing the pressure in the lower reservoir in line with water injection, but generally our model of the Hugon is very pressure insensitive. These last 2 points differ from the original narrative for Volve, which assumed good sweep in the lower 2 zones. No additional wells were drilled through this interval, so it is a modelling result that cannot be validated, except perhaps through some further scenario testing with flow simulation and history matching. Perhaps now, primed by our models, we can attempt to create maps of the vertically zoned reservoir sweep. We start by using 4D interpretation to more accurately segregate the reservoir. This creates an upper and lower reservoir SPA map. The upper map has hallmarks of a full reservoir original with the strong crestal response due to the Draupner, but we now see areas that appear unswept, although there remain questions about the imaging in the east. The lower reservoir appears to be an effective map of flood, with better balanced amplitudes that now favour the water injection locations. Mapping the lower reservoir 4D quadrature trough requires further work, but could be useful. We started out with the objective of deriving value from the 4D seismic, which initially looked difficult given the timing of the 4D relative to water breakthrough. Let us use the archetype 4D quadrature difference section from this presentation to help us illustrate what we have learnt. Firstly, with a calibrated 4D petroelastic model, we showed that the 4D response at Volve is dominated by water sweep. Then, by using 4D well synthetics in conjunction with RST logging, we have built confidence in the ability of the 4D seismic to help identify bypass pay in the upper Hugon. Lastly, the lower reservoir response was somewhat more complex and may require further modelling and assessment. This work has been valuable to us because it feeds into additional research by opening the following opportunities. We have used the higher vertical resolution of the 4D seismic to map the internal reservoir stratigraphy, which is not easily identifiable from the angle stack seismic cubes. And this in turn has allowed us to generate improved 4D maps for use in history matching of the flow simulation model. This work was completed as part of the Edinburgh Time-Lapse Project Phase 7. We want to acknowledge all the sponsors who generously support this research. We also want to thank Equinor for releasing the Volve dataset and Mark Thompson for his special comments and insight. Thank you to colleagues and peers for your feedback and review. And finally, we acknowledge our software providers Schlumberger and Petrosys, as well as the Python open source community.